Okay, we're going to go ahead and finish up this review. So we're starting off with number 8. And number 8 says that the ages of people in a group are normally distributed, there is that word normally again, with a mean, so I'm going to go ahead and put this information, of 35.6 and a standard deviation of 6.7 years. We're going to round our answers off to the nearest tenth. So for part A says what percent of the group is between 27.9 years and 39 years of age. So there were 3 ways to find the values. Number 1, you could use the 8-part curve with the 34% and the 13.5, but it looks like if we add or subtract these values, it's not going to get us these exact values. So that's probably not the best way to go. And we don't want to use a z-squared. It didn't ask us. The actual most accurate way to do this is using your normal CDF in the calculator. So what I'm going to go ahead and do is put in this into the calculator using normal CDF. And keep in mind that the order is lower, upper, mean, standard deviation. So since this is in between, our lower is 27.9, our upper is 39, our mean is 35.6, and our standard deviation is 6.7. So that's what I'm going to be putting into the calculator, and it should tell me the value for it. Okay, so we're going to go ahead and hit the second button. If you don't remember, second, I'll push this up. Second, and then you have to hit the distribution button, which is right next to the clear. And we want not the PDF, we want the CDF, which is number 2. All right, so the lower number we're going to change to be 27.9. The upper is 39. Standard deviation is 35.6. And then our mean is 35.6, and our standard deviation is 6.7. We're going to paste that in. So now it looks like this, and we're going to get a value of 0.569. And keep in mind that it's asking for the percent of the group. So I'm going to go ahead and change that to a percent. So we want to say it's a 56.9%. All right, let's look at part B. It says what percent of the group is below 25 years of age? All right, so this is another normal CDF. And it does say that we want the value that's below 25. So the very left is going to be negative 10 to the 99. If we were going to the very right, it would be positive 10 to the 99. And then it's going up to 25. So it's all the way to the left up until 25. It has the same mean and standard deviation. And now we're going to change that in here. So don't forget to hit second, bars, hit the number 2. And then we're going to change this to say negative 10 to the 99. And then we want this to be 25. All right, so now we can paste this all and hit enter. So we get 0.057. And then this also, again, is asking what percent. So I'm going to change that to percent as 5.7%. All right, let's take a look at number 9. Okay, number 9 says that a study is conducted by having teachers ask students how many hours they spend on homework each week. Why are the results likely to be inaccurate? And how could accuracy be improved? Well, if the teacher is asking the students how many hours you're spending on homework each week, and you don't want to say none because you might think that the teacher might say, well, that's why your grade is where it's at. That would be considered interviewer effect. So that's why this might not be accurate. Okay? So I would say that this is interviewer effect, where the student might not want to say how much they spend on homework truthfully. Okay. Yeah. All right. And then how could accuracy be improved? Well, there's actually multiple ways you could do this. You could have the students answer anonymously by putting on a paper, passing it up, doing maybe a Google form where your name's not attached to it. So I would probably say something that would help this be more accurate is by doing some sort of anonymous survey. Use anonymous survey to improve accuracy. Okay, and there's more than one answer that you could have had. All right, let's go ahead and go on to number 10 here. So suppose that the owner of a chain of clothing stores wants to know whether keeping his stores open an hour later on weeknights will increase total revenue. All right, so let's go ahead and take a look at the first thing here. It's saying, what is the treatment for this experiment? So what is he going to change to make this work? So I'm looking at this treatment as basically being open an hour later on weeknights. So you can't just say open an hour later. It's an hour later on weeknights. So to open an hour later on weeknights. Okay. And then for part B is what's the characteristic of interest? Well, you want to be open an hour later on weeknights to figure out what? We want to figure out if it will increase our total revenue. We want to see what's happening with this total revenue. Part C is what is the control group? So if we have control group. So the control group is basically keeping the store on its regular hours. Keep the store open for its regular weeknight hours. And so then part D is the treatment group. And so this kind of should go along with the treatment. The treatment is to be open an hour later on weeknights. So the treatment group is the stores that are open 1 hour later on weeknights. Okay. All right, let's go ahead and go on to this next part. So some professional sports teams test for illegal substances in players. The Play Clean test claims to detect an illegal substance called Performance X. Play Clean's developer tests their product on 1,000 people. Of the people tested, only 2% had Performance X in their system. Of those people that had Performance X in their system, 87% of them tested positive using the Play Clean test. For those that did not have Performance X in their system, the Play Clean test accurately tested negative 90.2% of the time. So our first step is to fill in this table. So I'm actually just going to fill it on here. So we know that it had a total of 1,000 people. of the people tested, 2% had Performance X in their system. So they're Performance X users. This is going to be 2%. I'm just going to put the percentage in. We'll figure it out in a little bit. Of those that had Performance X in their system, 87% tested positive. So tested positive, this will be 87% of this 2%. For those that did not have Performance X in their system, the Play Clean accurately tested negative, so we're going to say negative 90.2% of the time. All right, let's go ahead and put in some values here. So 1,000, and then we were going to find out what 2% of that is, which is 20 people. Of those 20 people, we want to say that 87% of them tested positive, which should be 17 here. So if there's a total of 20 and that's 17, this has to be 3. Okay. All right, so since this is 20, the rest of this will be that they never used it, which is subtracting 20 from 1,000. That gives you 980. And 90.2% of these are negatively tested. So 980 times 0.902 gets us about 884. So if you subtract 884 from 980, you get 96. And you can add the totals going across. So 17 plus 96 is 113. 3 plus 884 is 887. All right. Now that that table's filled out, let's go ahead and use that information to find some probability. All right, so let's do this first one. So it says part B, this is for number 11. Find the probability of having Performance X in the system given they are tested positive. So think about your Performance X being your A and the testing positive as B. So I'm going to do the probability that the Performance X is in the system. So X, Performance X in the system given that they test positive. So I'll put test positive kind of as abbreviation. So to find this, we're going to go ahead and look in the table where these two meet up. They are Performance X users and they test positive. So Performance X users test positive, that's 17. It's 17 out of, and don't forget that when you have that word given, that means that this is going to be on the bottom, the total number of people that tested positive. So the total people that tested positive is right across here. That's 113. So let's go ahead and see what that is in a percent. So we have, oh, it says probability. So actually we should just have it as a decimal. Okay, so we have 17 divided by 113. So that's going to be 0.15. Oh, it says round off to the nearest whole percent. Never mind. So 0.15 is the same thing as 15%. All right. Oh, there's no part. Okay, so now we're on number 12. Says that a restaurant has a beverage machine that works well 90% of the time. The owner bought a new beverage machine that works well 94% of the time. Each machine is used 50% of the time. Find each probability to the nearest tenth. So let's go ahead and make a little kind of diagram to represent this. So we have a beverage machine. Kind of think of that as the top. And from there, we have, it works well 90% of the time. And the owner bought a new beverage machine. So we're going to have the old machine. And we're going to have the new machine. All right. We know that the machine, this original machine, works well 90% of the time. So I'm going to go ahead and put 0.9 here. The owner bought a new barber machine that works well 94% of the time, so I'm going to put 0.94 here. Each machine is used 50% of the time, and we want to find out, oh, whoops, this is not quite right. Sorry, that's going to be down below. This is how much it's used. We are actually using this half of the time. So I'm going to put 0.5 here and 0.5 here. And then the fact that it works well. So this is works well. And this one is not well. And this is works well. And this is not well. Okay, so we know that the old machine works well 90% of the time. So here's our 0.9. And that means that 10% is not well. The new machine works well 94% of the time, 0.94, which means not well is the 0.06. Okay. So we're going to find the probability here. So for part A, it says find the probability that the old machine malfunction. So what we want to do is we want to take the old machine, find out that route from the very top. So old machine, and it malfunctioned, means it didn't do well. So we have 0.5 and then times 0.1. Now that's the top divided by the fact that it's all of the total ones that are not well. So we're going to have to take this path, 0.5 times the 0.1, and add to that the not well on the other side, which is 0.5 times 0.06. Okay. And this is using Bayes' theorem. So probability that the old machine malfunctioned over all of the malfunctions, old machine, new machine, and you have to add those together. All right, so I'm going to go ahead and put this in the calculator. So we have, let's see, move this up. Maybe I'll move it right there. Okay, so I'm just going to put it in as a fraction so it looks like that. So we have 0.5 times 0.1, and then on the bottom I have 0.5 times 0.1 plus 0.5 times 0.06. And that's going to get you 0.625. And since they want this probability to the nearest tenth, I'm going to go ahead and say, hold on, sorry. Here we go. I'm going to go ahead and put this to the nearest tenth. So you could either say 62.5% or 0.6. I believe I had 62.5% to the nearest tenth. All right, part B. We want to know if the new machine malfunctioned. So again, it's about a malfunction. So the denominator is actually essentially going to be the same between A and B. The difference is the numerator will be the fact that the new machine malfunctioned. Okay, so the new machine malfunctioning now is 0.5 times not working well, 0.06. And we're going to divide that by the fact that we have the new machine that didn't do well and the old machine that didn't do well. So 0.5 times 0.06 plus the old machine, 0.5 times 0.1, not doing well. So let's put that in the calculator. Since the denominator is the same, I essentially am just going to change this 0.06 instead of 0.1. Oops, not 66, 0.6. All right, so that's going to get you 37.5. or you could say 37.5%. And then part C, let's go back up here, says that the old machine actually worked well. Old machine working well out of working well in general. So let's go ahead and look at this chart. Old machine, 0.5, working well, 0.9, out of all the working well. So 0.5 times 0.9 plus the working well on using the new machine. 0.5 times working well is 0.94. Okay, so let's put that in the calculator. So we have 0.5 times 0.9, and then on the bottom 0.5 times 0.9 and 0.5 times 0.94. So I get a total of 0.489, which is 48.9%. And the last one of these is finding out what? The new machine worked well. All right, new machine working well. So let's go ahead and take a look at the new machine working well. I thought that was part C. New machine, yeah, new machine working well. That last one was old machine working well. So new machine and then working well. So 0.5 times 0.94 divided by just working well in general. So working well in general means we're going to say the same thing, 0.5 times 0.94, but we're going to add to that the old machine working well. So old machine is 0.5 times working well is 0.9. So essentially we're just changing the numerator to be 0.94. And that's going to get us 51.1. I'll put it in decimal first, 0.511, which is 51.1%. All right, and the last one of these. So we have a small apartment building. Oops, you guys can't see that, huh? A small apartment building has 2 washing machines. Washing machine A malfunctions 13% of the time. Washing machine B malfunctions 18% of the time. Washing machine A is used 60% of the time. We can use Bayes' theorem to find each probability. So here we have washing machines. This is number 13. So we have the washing machine. We have washing machine A, and we have washing machine B, and washing machine A could either work well, or it could malfunction, and B could work well, or it could malfunction. And let's put some values in here. Okay, so washing machine A malfunctions 13% of the time, 0.13. Machine A malfunctions 13% of the time. Washing machine B malfunctions 18% of the time, 0.18 here. Washing machine A is used 60% of the time, 0.6. And so if washing machine A gets used 60% of the time, that means 40% of the time is washing machine B. If it malfunctions 0.13, then you're going to subtract that from 1, and you're going to get 0.87. Over here, you have malfunctioning 0.18 out of the time, and so you're going to subtract that from 1, and you get 0.82. Okay. So we're finding the answer to the nearest tenth of a percent again. So let's look at part A. that machine A malfunctioned. So here's machine A malfunctioning. So it's 0.6 times 0.13 divided by just malfunctioning in general, both malfunctions. So we're going to still use the 0.6 times 0.13, that's using machine A, but we have to add to that machine B malfunctioning, 0.4 times 0.18. All right, let's go ahead and put that into the calculator. So we have 0.6 times 0.13, and then we have 0.6 times 0.13 plus 0.4 times 0.18. That gets us 0.52, and that's 52%. Let's say as nearest tenth, you can put 0.0 if you want after the 52. All right, part B, machine B malfunctioned. Okay, so the only thing that changes is really the numerator. So we're going to start with B malfunctioning. So that's going to be 0.4 times the 0.18, and then divided by the malfunctioning for both. So 0.4 times the 0.18, I should say, plus A malfunctioning, which is 0.6 times 0.13. All right, so I'm going to go ahead and change that in the calculator. And I'm going to change this numerator here to say 0.4 times 0.18. The numerator, or the denominator should be the same. So that's 0.48, which is 48%. Okay, so that's everything. If you get a chance, go back into your notes and see if you can do some extra practice problems. And I will see you on Friday.